Hello again. This is Professor Carlo, continuing with the lectures for Physics 1102. In the last lecture, we considered light as an electromagnetic wave. So an electromagnetic wave consists of electric fields and magnetic fields perpendicular to one another, varying sinusoidally in time, and these travel through space. And they travel through space with a speed given by c, the speed of light in a vacuum. Light also has particle-like aspects, although that's something that we really won't consider. What we're going to do for now is we're going to think about optics within a very specific set of limits, and this set of limits is known as geometric optics. Now, essentially the way that geometric optics works is we're not going to think too much about the wave-like characteristics of light. So because light is waves, you have phenomena like interference and diffraction that can result in complex behavior. Chapter 25 of the textbook does go into this, but we're not going to talk about that in this course. Instead, we're going to consider the simpler case in which light is assumed to travel in straight lines. So we think of light as composed of these things which we call rays, and these rays, in general, will travel in straight lines from point A to point B. This is the assumption of geometric optics, and as you might guess from the name, we're going to be using a lot of geometry. We're going to be calculating angles, we're going to be drawing diagrams, there will be triangles, and all of that other fun stuff is going to come back. So, a few simple ideas that come up here. The first thing that we'll consider, and there are two primary phenomena that we'll talk about, and these are reflection and refraction. So reflection is what happens when light hits a reflecting surface, which I'll draw here. This is a mirror. We're going to have an incident light beam, which comes in like this. So this will be our incident. That's our incident ray. And now when this ray comes in, what we want to do is we want to look at the angle at which it hits. And this is very important. By convention in optics, we always measure angles from the normal, which comes up at a 90-degree angle from the surface. So wherever this ray hits on the surface, we draw the normal, and then we calculate the incident angle, which is measured from the normal. Now, the law of reflection tells us what happens to the ray when it reflects. So here is our reflected ray. And the angle at which this ray will reflect we'll call theta r. And the law of reflection tells us that theta I is equal to theta r. That's it. That's the law of reflection. The angle of incidence equals the angle of reflection. And again, the angles are always measured from the normal. So we could try to trick you. We could give you a problem where we give you the angle from the mirror itself. If we gave you that angle, then you'd have to do 90 minus that angle in order to get the normal angle. That's the principle of reflection. This brings us to refraction. So now, light has an interesting property. When light travels from point A to point B, it will always travel along the path which takes the shortest amount of time. Now, if you're just traveling through vacuum, the shortest time path is also the shortest length path, and the shortest length path is a straight line. And that's why rays tend to travel in straight lines. But if the speed of light is changing, if there's a different speed of light, and that's what happens inside a medium, the speed of light when light enters some medium is equal to the speed of light in vacuum divided by something called n, where n is known as the index of refraction. So this n is a number. Just to give you some values, for air, n is equal to 1.0003. So basically 1. Of course, a vacuum has n exactly equal to 1, which you can see from here. Water has N equals 1.33, so about 4/3. Glass comes in a variety of types, but typically N is on the order of about 1.5 to 2.0. The higher end is some really exotic types of glass that have heavy elements put in them, but typically about 1.5 to 2. So when light enters glass, it slows down by a factor of 1.5 to a factor of 2. So if I had an index of refraction of 2, the speed of light in that medium would be 3 times 10 to the 8 meters per second divided by 2, which would be 1.5 times 10 to the 8 meters per second. Diamond has N equals 2.4, and we're going to come back to that in just a little while, why that's important. In fact, in the next video when we talk about total internal reflection, I'll tell you why that's important. Diamond has quite a high index of refraction. Of course, it's very expensive, which is why we don't use it for lots of other things. But anyway, to understand the significance of this, I'm going to think about a very different problem. Let's say that you're a general and you have a bunch of troops who are stationed up here, and you want to get those troops over to there. So we're going to start at this point, we're going to end at that point. Now, if this were just a wide open field, if this were some straight uniform path, the shortest and fastest way to get your troops from A to B would simply be to follow a straight line, which I will show in dots like this. That would be the shortest path from A to B. But let's say, for the sake of argument, that in the middle of this, and let's do this in a slightly different color to make it stand out. Let's say that in the middle of this, there's a big, nasty swamp, or there's a river or something. And the thing about this swamp is that it's really, really slow going. So getting through it means you gotta, trudge like this, and you're going really, really slowly. Maybe you're hacking your way through brushes and things like that. So it's really, really slow to get through that swamp. So the shortest path, or I should say the least time path, the quickest path, which may not be the shortest in terms of distance, will involve trying to minimize your time in the swamp. And the way that you would do that is probably something like that. So we would go a little bit away from the dotted path in order to shorten our path through the swamp. Or if I were to draw the normal vectors, there's going to be an angle of incidence over here, and there's going to be an angle of refraction over there, and we can see that those are going to be unequal to one another. And in particular, because the swamp is slow going, we see that the index of refraction, or the angle at which I enter the swamp, is going to be smaller, that is closer to the normal, than the angle at which I came in on the other side. Now, the relationship between these is called the law of refraction. So here, if I have some refracting interface here, this has an index of n1, this has an index of n2. If one of these was air or vacuum, the index would simply be 1. So here comes my incident beam. Here's my incident ray, and here is my refracted ray. If I were to draw the normal here, there is my incident angle, again measured from the normal, and then in here will be my refracted angle, and the relationship between these is that n1, the upper refractive index, times the sine of theta I, which is the angle on the upper side, is equal to n2, which is the lower index multiplied by sine theta r. So that's the relationship between the two of those, and I'm going to put this in a box since this is one of our important results, and I will also put the law of reflection in a box. So the way that I would use this is, if I know the two indices of refraction and I know one of these angles, I could figure out the other one by algebraically solving. Or conversely, if I knew both of the angles and I knew one of the indices of refraction, I could find what the other one is. So in general, and this is the rule that you can kind of keep in mind, is that when you start from a medium with low index and you're entering a medium with high index, so again, low n moving into high n, the light will bend towards the normal in order to try to minimize the path through that higher index where it's slow going. The reverse case is also true. If you go from a high index to a lower index, the light is going to bend away from the normal, and that is what we're going to consider in the next video. So that is the law of reflection and the law of refraction. These are basically the rules of the road which we're going to use in order to solve our problems in geometric optics. We're going to consider reflection from flat surfaces like this. We'll consider reflection from curved surfaces, which makes it a little bit more complicated. We'll consider refraction through flat plane interfaces. We'll also consider refraction caused by lenses which have curved shapes, and these have the ability to focus light, can produce images. They can produce magnification, they can produce upright images, they can produce inverted images, and that is what we'll take up in chapter 26. So that's it for this lesson, the law of reflection and the law of refraction. Thank you, and in the spirit of contactless greetings, I will say, live long and prosper.